When a single node database attempts to process an overwhelming volume of incoming queries, it eventually runs headfirst into a hard physical ceiling. No matter how robust the machine, it remains a single point of catastrophic hardware failure. You can vertically scale a server by adding more memory, faster disks, and additional CPU cores, but those upgrades offer diminishing returns. Eventually, the hardware simply cannot process the incoming read and write throughput. To bypass this physical limit, engineers rely on replication. This is the practice of maintaining exact copies of a single dataset across multiple network-connected machines. Replication solves three distinct engineering objectives. First, it reduces geographic latency. By placing a copy of the database closer to the end user, you physically shorten the distance packets must travel over the network. Second, it provides high availability. If a local power grid fails or a hard drive degrades, identical copies of your data remain online and accessible elsewhere in the system. Third, it allows you to horizontally scale your read throughput. Instead of one machine handling every incoming search query, you distribute that exact same workload across 10 or 100 separate nodes. Operating a database on a single node guarantees simple state management. Distributing that database across a network abandons that simplicity, trading it for the scale and survivability that modern applications require. Replicating static, immutable data across a network is a trivial operation. Copying a rigid archive file from one server to another is a solved problem. But live databases do not hold static data. They are highly dynamic environments, absorbing a continuous, high-volume stream of concurrent mutations from thousands of clients at once. If you allow multiple nodes to accept write requests simultaneously without strict coordination, you immediately invite race conditions. Two clients might attempt to update the same row on two different machines at the exact same millisecond. Because network latency is variable, these conflicting updates will propagate across the system at different speeds. The order of operations gets scrambled, and your replicas will silently diverge into irreconcilable states. The engineering challenge of database replication lies in establishing a single, deterministic order for data changes that every node in the network agrees upon. This diagram illustrates the industry's primary solution to the mutation ordering problem, the single leader topology. By designating exactly one replica as the leader, the system forces all incoming write traffic through a single node, acting as a strict gatekeeper. When a client sends an update, the leader executes the change locally, committing the primary key, the old value, and the new value directly to its own storage first. Once the leader records the change, it packages the exact mutation into a continuous sequence known as a replication log. It then transmits this log across the network to the other nodes, which act exclusively as followers. Because the leader has already serialized the changes, the followers simply parse the log and apply the mutations to their own local disks in the exact deterministic order established by the leader. With the state successfully synchronized, clients executing read-only queries can target the followers directly, removing the read burden from the primary node. By routing all writes through a single bottleneck, this architecture deliberately sacrifices write scalability. In exchange, it guarantees a unified, deterministic history of state changes across the entire cluster. This sequence diagram maps time along the horizontal axis to illustrate a critical timing problem. When exactly does the leader tell the client that their data was successfully written? Synchronous replication prioritizes safety. The leader processes the write, sends it over the network, and then completely halts. It will not return a success message to the user until follower 1 explicitly confirms it has secured the data on disk. This provides a durability advantage. If the leader's hardware suddenly fails, you know with absolute certainty that your committed data is safe. But it creates an availability risk. If that synchronous follower crashes, or a network partition delays its response, the leader must block all incoming writes. The entire database grinds to a halt, waiting for a node that cannot reply. Asynchronous replication prioritizes speed. Look at follower 2. The leader fires off the data change and immediately confirms success to the user, without waiting for the follower to respond. This maximizes system performance. The leader continues executing writes at peak throughput, unaffected by downstream network latency or lagging followers. The cost is data durability. If the leader crashes after confirming the write to the user, but before the asynchronous stream reaches the follower, that data is permanently lost. Engineers must balance these extremes. Databases are typically configured to be semi-synchronous, maintaining exactly one synchronous follower to protect against a single node failure, while keeping the rest asynchronous to ensure the system remains available. Expanding a cluster requires bringing new followers online, but executing a standard file copy from the leader will corrupt the data because the live database is in constant flux, processing writes mid-transfer. To correctly bootstrap a node without taking the system offline, you take a consistent point-in-time snapshot of the leader, copy it to the new hardware, and then the new node requests the specific backlog of data changes starting from an exact log sequence number. A similar process, called follower catch-up recovery, happens when an existing node reboots. It checks its local disk for the last processed transaction, reconnects to the leader, and requests the missing changes to bridge the gap. But the true crisis scenario is the sudden, unexpected failure of the leader node itself. Surviving this requires an automated process called failover. First, the followers detect the failure by relying on strict network timeouts. If the leader misses a heartbeat ping, it is presumed dead. Second, the remaining nodes enter a consensus process, communicating to elect the follower with the most up-to-date replication log as the new leader. Finally, the system must reconfigure client request routing, forcing all applications to send their new write traffic to the newly promoted node. Automated failover is highly dangerous. If the original leader was merely delayed by a network spike rather than dead, it might come back online still believing it is the primary node. This split-brain scenario can cause both nodes to accept conflicting writes, proving that while failover keeps a system alive, it introduces systemic risk. Below the architectural topology, the stability of the entire system relies on the literal byte stream payloads moving across the network. In the simplest implementation, known as statement-based replication, the leader logs every SQL query, every insert, update, or delete, and ships that exact text to the followers to execute independently. Non-deterministic functions create immediate problems for this approach. If a query inserts the current timestamp or generates a random number, the leader and followers will evaluate those functions locally at different times, resulting in permanently divergent datasets. Alternatively, systems can use write-ahead log or wall shipping. This transfers the data at the lowest possible level, copying the exact byte modifications made to the disk blocks. While ball shipping guarantees exact copies, it intimately couples the replication stream to the storage engine. If the leader and followers run different versions of the database software, the disk formats won't match, making zero-downtime database upgrades impossible. The modern industry standard is the logical or row-based log. Instead of shipping physical disk blocks, a logical log transmits parsed, row-level data payloads containing just the primary key, the column, and the new value. By decoupling the log from the storage engine's physical disk format, logical logs allow the leader and followers to run different software versions. Replication transitions from being a brittle hardware mirror into an interoperable data pipeline. Zooming out, a single leader cluster functions by centralizing the source of truth. By forcing writes through a single node, we solve the race conditions of concurrent mutation. We establish a deterministic order of operations and use that order to horizontally scale our read capacity across multiple followers. The cost of this architecture is persistent vulnerability. The system relies on the stability of the network, and surviving a leader failure demands complex, risky failover automation. Furthermore, because systems must remain available to accept writes, relying on fully synchronous replication for all followers is impractical. Any single node outage would halt the entire cluster, making asynchronous streams and the latency they bring unavoidable. The single leader architecture does not eliminate state inconsistencies. It merely condenses them into replication lag. Ultimately, the database guarantees the order of writes, but it shifts the burden of dealing with slightly stale read data directly onto the application developer.